Done.
Thank you.
Welcome to everybody. So I would like to introduce you to the Young Seminar Series. I'm not involved today. We have two great organizers, so Sinia Kurishenko from Copenhagen Business School and Cristina Molero del Rio from Instituto de Matemáticas de la Universidad de Sevilla. They are both the organizers of this Young Seminar Series. They are meant to present the latest research of junior academics, and our NeEDS project basically is giving support to develop other skills, which is also organizing this event, and they have done in a marvelous way. Thank you so much, and I give the floor to Sinia.
Thank you, Dolores. So I will introduce a little bit each speaker to you. And the first speaker is Cristina. Cristina Molero del Rio. She is, as was taught, a PhD student at IMUS. And her supervisors are Emilia Carrizosa and Dolores Romero Morales. They are also organizers of these seminars, and Rafael Blancuro. And today she will present the paper, Mathematical Optimization in Classification and Regression Trees. So, floor is yours, Cristina.
Okay. Thank you. Well, I'm trying to share, but it's not working. Okay. Wait, one moment. Okay, it's not working, so I'm going to use the PDF that we have uploaded. I hope you can see it.
Yes.
Yes.
Is it? Okay. Okay, Sinia, thank you for the introduction, and hi, everyone. This research I'm going to present today is a joint work together with my supervisors. So let's start by recalling how classification and regression trees are traditionally built. Imagine that it is interesting to know the policy that a certain bank takes into account when granting a loan as a function of the age and the income level of their applicant. So on the left side, we have a sample of 10 former applicants, and on the right side we have its corresponding classification tree. As we can see, a classification tree is nothing but a recursive partitioning of the whole training sample into a smaller and smaller subsets of individuals that we call them nodes. These sets are generated by imposing some condition splitting rules on the predictor variables in the model. And then each leaf node will have associated a class label in case of classification, which corresponds to the majority class. Is there any problem? Ah, okay. So in classification, we have a class label, which is the majority class within the individuals falling in that leaf node. And in regression, we usually have the mean of the values of the response variable. Popular tree methods like cards employs low computational efforts, but at the expense of a greedy procedure. So where each splitting rule is made, but in a forward stepwise search, so we do not ensure that the decision made is going to be optimal in future steps. So in Both advances in computers' performance and optimization solvers have led to a growing research on building optimal classification and regression trees, as we review in our recent articles, where you can see that the grid part of proposal are based on mixed integer linear optimization. This formulation requires decision variables to define the topology of the tree, as we will also do, but they also need binary decision variables that are going to be associated to each individual in order to model the path each of them follows down the tree. We will see that this linear dependence is not in our, this linear dependent on the size of the training sample is not in our proposal. There are other paradigms like constraint programming, dynamic programming, or SAT that have been proposed to handle, to build classification and regression trees. Now our model, you can see our proposal in these works that I referenced here. The main characteristics of our trees is that we model probabilistic splitting rules as opposed to deterministics. Our formulation is continuous, and we build a tree by seeking a compromise between two objectives, which are accuracy and local and global sparsity. Additionally, we will see the strength of our formulation, and we are going to model some desirable properties that we can add to our model, which are local interpretations, counterfactual explanations, and cost sensitivity and fairness constraints. Sorry. We are going to construct our trees. We depart from a sample of n individual where P predictor variables are measured, and each individual has associated a class label in case of classification, or a continuous measurement in case of regression. We want to build a maximal binary tree of depth D. So the set of branch nodes are known in advance. Here, the nodes 1, 2, and 3, and the set of lead nodes also are known, which are 4, 5, 6, and 7 in this example. Here, prediction is randomized. At each branch node, we will have, for each individual I, a probability of going down the left branch node and a probability of going down the right one. So in the end, we will have in each leaf node won't contain a subset of individual as cards, but all the individual with a certain probability. And then the prediction made at each leaf node will be found by optimizing the two criteria that we have previously defined. In our model, we allow for oblique splits. That is, more than one predictor variable could take part in the splitting rule. So we need to define decision variable AGT, which is the coefficient of predictor variable J at branch node T, and mu T, the intercept of the oblique cut. As I've said, opposed to deterministic approach, we are represented in this image by the orange line. The yes/no decision rules in our approach is being replaced by a probabilistic cut, which is induced by the inclusion of a smooth cumulative density function of a continuous random variable. We will denote it by F. So we will have PIT, which is the probability of individual I at branch node T going down the left branch, which is the calculated as the cumulative density function evaluated over the oblique cut. And the complementary probability will be the probability of being down or going down the right branch. Then we have capital PIT probabilities, which are the probability of individual I to belongs to leaf node T, which are just product of the previously defined probabilities. So it remains to be defined the prediction made at our leaf nodes. So for that, we need to define the decision variable CKT, which stands for the probability of being labeled at class K, given that we are at leaf node T. And we also have to impose the constraint you see there to ensure the probability distribution. As you can see, we have three terms in our objective function. First, the misclassification error, and then local and global sparsity. In the local sparsity term, what we want is less predictor variables to be involved in each splitting rule. And in global sparsity, what we seek is less predictor variables across the whole tree. Okay, for that we need the infinity norm. We can see that there exists an equivalent nonlinear smooth formulation of this problem with linear constraints. And if you see the range of the decision variables, there is no decision variables that is directly linked to the observation, as opposed to Milo approaches, as we have said before. In case of regression, we also have these properties, and as customary, we minimize the mean square error together with the local and global sparsity terms. For the mean square error, we need to define which is our prediction at each leaf node. Here, instead of considering a constant prediction, we also allows the model to give a linear prediction. So for that, we need to define these new A tilde and mu tilde decision variables, but that are also continuous. Okay, so the next 4 slides, I'm going to focus on classification. To model the desirable properties that we can handle with our formulation. First of all, it is important to note that our prediction is smooth against the other approaches. Suppose that we have the optimal solution and we have an incoming individual with predictor vector X, then we have the probability of belonging to class K is the one that is shown there. Where capital PXT is defined similarly to capital PIT, as we have seen before, it was the products of small PIT, which were the computation of the cumulative density function. Okay, and we saw that, well, we assumed that this cumulative density function was smooth. So because of that, we can see that PK is also smooth in the continuous predictor variables. That means that even small changes in these variables will produce changes in the value of PK. And why it is important, this smoothness? This is crucial in order to be able to provide local interpretation of the tree model. So imagine we have an individual with predictor vector x0. So we could linearize this PK close to x0, okay, having that expression there. So the matrix of the partial derivatives, the coefficients on here, give information on the sensitivity of the class membership. Okay, so around x0. So this what this means is that for any individual, we could perform a full sensitivity analysis to study the impact that each continuous predictor variable has on the probability of class memberships. Even more, we can also provide counterfactual explanations. We have an individual with predictor vector x0, and we wonder what are the minimum changes to the predictor variable such that the individual is predicted to be in another class k star. So indeed, if we define a norm and a set of allowed movement from x0, one can solve a nonlinear problem of the form that is shown there. And these two characteristics are because of the smoothness of our approach. As I've said, Milo approaches cannot handle this, but also we can model cost sensitivity and fairness. For cost sensitivity, well, at times there are groups of individuals in which predictions error are more critical. For example, in medical diagnosis with healthy and unhealthy people, it is more critical to say to an unhealthy patient that it is healthy, okay, because the risk will be higher. So it is then more adequate not only to focus on the overall prediction accuracy, but instead ensuring a certain level of performance over that class. For example, if K was the unhealthy class. And this it is just a constraint that has to be included in our formulation. In case of fairness, fairness is referred to avoiding that the outcome of the model discriminates group of people sharing sensitive features such as gender or race. So suppose that we have a group S of individuals to be protected against discrimination. So we may impose that the average probability of being assigned to class K for an individual in S does not differ much from the average in the whole training sample. In the follow, yeah.
It's already 15 minutes, so if you...
Okay. So yes, I am going to take 1 minute just to summarize here.
Yes,
what you can see is that we have done a numerical result for classification and for regression, and we have benchmarked our approach with many methods. And what we can see is here for regression also. Here I have highlighted the best methods. What I show is that our proposal is on the top together with random forest and a local search procedure that cannot handle the properties that we have already defined. Okay. So some conclusions. I have presented a continuous optimization approach to build trees with probabilistic cuts. We have seen that it is flexible enough to incorporate cost sensitivity and fairness constraints. The smoothness of our approach allows us to provide local interpretation and counterfactual explanation against the Milo approaches and deterministics one. And empirically, we we are comparable or outperform the benchmark. For future research, we would like to deal with functional data, and also it is interesting to try to embed our approach in bugging or boosting ensembles. Here the bibliography, sorry, and just a slide to thank you for your attention. Thank you.
Thank you, Cristina. I'm not sure that we have time for questions right now. Don't you mind if we postpone this to the end of the all talks? Okay.
Okay.
So if anybody has questions, you can ask them in the end of session. So now it's turn of Asunción, Jiménez-Cordero. She postdoctoral researcher in research group optimization and analytics for sustainable energy system, OASIS, am I right? And this is under University de Malaga in Spain, and she's working together with Juan Miguel Morales, and he will also present on this seminars series on March 22nd. So the floor is yours. I hope you can start sharing the...
Yeah, I will try to share my screen. I don't know.
Perfect.
Can you see? Okay. Can you see my slides?
Yes. Yes. Perfect. Thank you.
Okay. Perfect. I will try to put this here. Okay. So thank you very much for the presentation, and thank you all the organizers and the NeEDS project for inviting me. Well, my name is Asunción Jiménez-Cordero, and I'm going to present this work, this joint work, together with Juan Miguel Morales and Salvador Pineda. The three of us belong to the OASIS research group, and if you want to know more about what are our research topics, I suggest you to visit the webpage. And today I'm going to talk to you about about feature selection in nonlinear SVM using a novel min-max approach. Okay, so this is the outline of the presentation. So I guess most of the attendees know what SVM is, binary classification and all these things, but I want to give you a brief introduction of this. Then I want to formulate you the approach, our proposal, which is based on a min-max optimization problem. Then I will explain you how we reformulate the problem to solve it. And then in the two last sections, I will tell you about the numerical experience and conclusions and future research. So, well, in this talk, I'm going to talk you about the binary classification problem that is very simple. So we just have two different groups, in this case, the blue dots and the red ones, and we want to find a linear classification rule in such a way that when a new individual comes, we are able to know to which class it belongs. So in this case, it's clear that it belongs to the blue class. But the point is that we are not only interested in knowing this linear classification rule, but also to know the classification rule with a lower number of features. So in this case, it's clear too that the first variable, so the x-axis, is the one that is more important to classify. And to the same, we are going to use the well-known technique supervector machines that among all the possible hyperplanes that we can find, it aims to find the one that maximizes the so-called margin. And these 2 points where the margin lies are called supervectors. Okay, well, here in the previous slide, I show you an example where the points can be clearly classified by a linear hyperplane. Sorry, but what happens in the nonlinear case? Well, SVM also works in this case, and it just define a feature map that features the points to a high-dimensional space where the points become linear, and therefore we can find this linear hyperplane. So this is more or less the motivation behind the problem. So the aim of this work is to develop a new mathematical optimization framework in a way that we can handle the nonlinear SVM classification problem at the very same time that we select the most important features. And to do this, we are going to apply a min-max approach. So what is done in the literature? There's a lot of works relating SVM classification and feature selection in the linear setting, and also in the nonlinear one, that is the setting that is important for us. So we can divide all the works into filter methods, such as this kernel polarization that is very fast, but do not take into account the classifier information. The rubber methods are similar. One of the most famous one is the RFE, but it has the disadvantage of fix a priori the number of selected features that we want to select. We don't like this part. And the embedded method, there are a lot of works related this kind of this class, but the point is that most of them use or need to carefully tune several hyperparameters and need ad hoc approaches that are not very easy to understand. So the contributions of our work is that we want to develop a new embedded feature selection method where the features are not fixed but provided by our approach. And the point here is that we just need the use of off-the-shelf solvers, and no ad hoc strategies have to be used. So here we have a bit of notation. So the data are denoted by xi, and each individual has associated a class label yi, which is denoted by -1 or +1. And this is the mathematical formulation of the SVM problem. It says here basically that we want to maximize the margin, which is equivalent to minimize this objective function here, and the constraints essentially says that the point should be correctly labeled. So this is the mathematical formulation in the linear setting, and in the nonlinear one, as I have told you, we have to include this feature map phi. But the point here is that we are not, as I told you before, we are not only interested in binary classification, but we want also to select features. So we want, among all the possible phi functions that are available, we want to select the one into a functional space parameterized by this gamma variable, and we want to minimize over this decision variable. What is the bad part here? Well, that we usually, we don't know the phi function, and we don't know neither the structure of this functional space. So what we do is to forget, is to say, okay, we want to forget, or we want to replace this phi function but something that I know, and we use the dual. We replace this inner level problem by the dual FCVM. And we have here to minimize the dual of the SVM problem. And here we note that instead of knowing the explicit value of the phi function, we just have to know the dot product between these two phi functions, what is called the kernel trick. So we replace this dot product by the kernel. Okay, there are several kernel functions that we can use, and in this work we choose the anisotropic Gaussian kernel, where we have one gamma value per each one of the features, and this gamma value plays the role of the importance given to the feature j. So if gamma j tends to 0, that means that this feature plays no role in the classification. And if gamma is very large, that means that it's very important when classifying. But we have to be careful, because if all gamma are 0, then that means that all points will be classified in the same class, and we don't want that, this. And if gamma j tend to infinity, then we will have overfitting. So it seems that we want a model that model or that formulate a problem with a trade-off between the model complexity and the classification accuracy. And this is exactly what we do. So this is the problem formulation that we propose, where we have here to minimize in gamma the dual of the SVM variable, of the SVM problem, sorry, and this part is related with the classification accuracy. We add a new term, which is related to the model complexity, that is nothing but the norm P of the gamma variables. And we add here two terms, the convex combination, to do a trade-off between the model complexity and the classification accuracy. So the higher the C2, the more simple is the model, and the lower the C2, the more important I will give to the accuracy. How we so this problem is difficult to handle, because it's a min-max optimization problem. It's non-convex, non-linear, all these things. But we reformulate it into the single-level equivalent problem formulation using different steps. So in the first one, we use the epigraph form, and we just define a new decision variable set by stating and putting it in the objective function, and say that this set decision variable should be greater or equal than the dual of the SVM problem. Then, since the dual of the SVM problem has a quadratic objective function with linear constraints, we can use all the theory of all the duality theory, and this is exactly what we do. So we define the dual decision variables for each one of the constraints, and we compute the dual of the lower level problem here. Well, this is the standard form to calculate the dual, so we use the Lagrangian, and here just some notation. So this G gamma is nothing but the product of these matrices here, where the kernel appears here. This is the dual of the lower level problem, and we can replace this lower level problem by its dual. Okay, and now since we have to minimize a function, a decision variable, which is lower bounded by this minimization optimization problem, we can replace this by the objective value, remaining this final single level optimization problem. Okay, so just to recap all the steps that we have performed. So here is the initial min-max reformulation, then we use the epigraph form, then thanks to the strong duality theorem, we can replace this maximization problem by the corresponding minimization one. And this is the final single equivalent reformulation. What about the numerical experience? Well, even though we have reformulated this problem, it's even very hard to solve, because we have two hyperparameters here. It is nonlinear, non-convex. So, but the point here is that we use off-the-shelf solvers to solve it. And the strategy that we propose is very simple. It is just based on grid search plus a local solver, and all this is embedded in a k-fold cross-validation. So we have tested our methodology in 4 datasets from the UCA repository, but just for the sake of illustration, I'm going to show you the results just on the first dataset, on the breast dataset. In this first figure, we can see for different values of C2, we can see the norm of the weight in this dotted line and the accuracy on the test sample in this solid line. And we can see that this is not a surprise, that the higher the C2 value, the lower is the norm of the gamma. And here we can see that the solid line corresponding to the accuracy on the test sample is not so smooth as the other one. And this is due to 2 main reasons. So the first one is because we are plotting here the accuracy on the test sample, and we are training on the trained sample. But what I want to remark you is that for lower values of C2 that correspond to very complex models, and therefore to models that behaves very well in the training set, but not so well in the test set, as can be seen here, and also that for higher values of C2, the model tends to have 0 norm, and therefore do not take into account or do not pay many attention to the classification accuracy. Now we have fixed one value of C2. In this case, we have chosen C2 equal to 0.4, and we have compared our methodology with different strategies in the literature. So this NMFS, so min-max feature selection, correspond to our method, compared at first sight with the no feature selection method, which means that we forget at the feature selection and we just want to classify. And here we can see that both results are, both accuracy results are comparable, and this is very good for us because it means that our method is able to extract the powerful information but with a less number of features. In the second comparison, we choose a benchmark method in the literature, which uses an ad hoc strategy where not very complex, not very simple, heuristics, and we see here that our off-the-shelf strategy is comparable in terms of accuracy with the one in the literature that needs that need to tune a lot of hyperparameters. And for the sake of comparison, we have also test this very same benchmark strategy, but instead of using the ad hoc strategy, using off-the-shelf solvers, and you can see here that the results are very bad. Yeah.
It's time to wrap up.
Okay, just 1 minute. In the last one, we have compared with the off-the-shelf strategy SVM, L1 SVM, sorry, and we see here that the results are also comparable in terms of accuracy. So, since both of them are off-the-shelf strategy, we decide to perform new experiments. So we see here in blue the accuracy results of our method for different values of C. So each point or each triangle corresponds to a value of C, and here the accuracy results in black, but for the L1 SVM method. And we can see that our approach is able to have the very same results in terms of accuracy, but using a less number of features. And finally here, I just want to show you that our method is consistent when ranking the features. So we have shown here for different values of C2, the top 5 selected features by our method. And you can see that this set is more or less common for all values of C2, so it's consistent. And just if you want to know more details about this data set or other ones or the methodology, you can visit and have a look at the recently published paper. And just conclusions of future research, we have developed a new min-max optimization approach for select features in nonlinear SVM classification using off-the-shelf solvers. And our approach is competitive against the benchmark results. And as future research, we want to extend it to regression or clustering and to apply it to real-world applications to develop a new physically aware approach. And these are some of the references, and that's all. Thank you very much. And sorry for the delay.
Thank you. Thank you for your presentation. No worries. I think it's as before, we don't have time for questions right now. So we, if it's possible, please ask your questions in chat or maybe after the last speaker. And the last speaker is Connor Lawless. He's a PhD student from Cornell University in US, and he's supervised by Oktay Gunluk. And today he will present his talk on fair and interpretable decision trees for binary classification. Or decision rules, sorry. Yeah.
Awesome. Thanks for the introduction. Can everyone see my slides? I'll take the silence as a yes. Well, first of all,
yes, we can.
Massive thank you for inviting me to talk here. As Cristina mentioned, my name's Connor. I'm a PhD student in operations research here at Cornell University, where I am extremely lucky to be advised by Oktay Gunluk. And today I'll be talking about our joint work on fair and interpretable decision rules. So I probably don't need to convince anyone that machine learning has become pretty omnipresent in our daily lives. Everything from the photo tagging service on your phone to a spam filter in your inbox to your Netflix movie recommendations are being driven by machine learning algorithms. But one area where machine learning hasn't quite taken over, nor it should right now, is socially sensitive decision making. And to see why this is kind of a tricky problem, we can walk through an example. So the example that motivated us comes from a bank here in the US, Citizens Bank, and it's for approving loan applications. So right now, if you want to get a loan or a mortgage, you go to a bank, you complete your application, and some sort of bank official decides based on the merits of your application whether or not you should get a loan. So on a first pass, this might seem like a great application for machine learning. You have an awesome wealth of data that you can use to train your model. It's a lot quicker, more time efficient than employing 20, 30 people to be reviewing these applications. And in some sense, maybe it's more fair because instead of the different biases and whims of every person that's reviewing applications, you have one centralized system. But the issue with this kind of application is that the decision your model makes has a really high societal cost. So denying somebody a loan can have a really long-term impact on their financial future and their ability to move up in life. And because of that, it's really important that we need machine learning algorithms that aren't discriminating on the basis of protected characteristics like race, sex, immigration status, religious affiliation, so on and so forth. So that's the first technical hurdle. We need some sort of notion of fairness in our algorithms. A second hurdle is this idea of interpretability. So legislation like GDPR in the EU ensures that whenever we do automated decision making, the person that we're making that decision for has a right to some sort of explanation. And this is difficult because it rules out a whole class of machine learning algorithms like neural networks and random forests that are inherently uninterpretable in nature. And this really gives rise to our research focus, which is to design machine learning algorithms that are both interpretable and fair, specifically for use in these socially sensitive decision-making applications. Now, obviously, this is a pretty broad mandate. So for today's talk, I'm going to be focusing on this binary classification setting. So as Asunción talked about, binary classification setting, you have one of two possible labels, yes or no, true or false. Somebody can repay a loan or they can't. And you're going to make that decision based on a number of features that could be either real valued or categorical. The next thing we have to answer is how we're going to do this interpretability. And there's a couple different schools of thought on this. One method would be to take a really powerful black box neural networks or random forests and try to build some sort of model to explain it. But instead, what we do is we focus on just learning an interpretable model class. And the interpretable model class that we focus on are Boolean rule sets. So this might be a bit of a review for people that were here for Ilker's talk a few weeks ago. But essentially, a Boolean rule set is just a set of rules in disjunctive normal form, which you can think of as OR of ANDs. So each rule is just going to be a collection of conditions that are going to be satisfied if all the conditions are met. So in this example down here, the first rule, the conditions could be that the third feature is greater than or equal to 3, and the second feature, or the 21st feature, is greater or less than or equal to 28. And for our decision set, we're going to classify a data point as having the positive response, so 1 or true, if it meets any of the rules in the set. And the idea is going to be that the less rules we have with the less clauses, the more interpretable our model is going to be. One additional technical assumption we make on our data is that all of our features are binary valued. So instead of having real valued features and categorical, every column is just zeros and ones. And this may seem a little onerous, but there's actually a lot of strategies we can use to transform categorical and numerical data to be binary valued. So for categorical features, we can use what's called one-hot encoding. So essentially, we're going to create a new feature for every possible category value, and then we're just going to put a 1 in the column corresponding to the original value. So let's say we had a feature on education level that could be high school, undergraduate, or graduate school. We would create one feature for high school, one feature for college, one feature for graduate school, and just put a 1 in the corresponding column. The other thing we do is we also add the complement of those columns. So we add a column for not high school, not college, not graduate school. And in that case, all of the values are 1 with the exception of the column corresponding to the original value. So in this case, if our original value was high school, then not high school column would be 0. And we can do a similar trick for numerical features. So what we're going to do is we're going to select a sequence of thresholds. For example, you can pick the deciles of that column. And essentially, we're just going to look and see if our value is less than or equal to those thresholds. So we'll add one column for each threshold value and just check if the original value is less than or equal each threshold. And similar to the one-hot encoding case, we're also going to add the complement. And if I've lost anyone in the last 2 minutes, no worries. I know this can be a little confusing on a first pass, but the takeaway here is that there's some pretty common tools that we can use to just transform our data to this binary case. And the benefit of this is extremely practical for us. So when you have only binary features, we now only have a finite set of possible rules. And a rule simply corresponds to just picking a subset of your features and checking that those columns have 1s for them. Great, so we have our problem, binary classification. We have our interpretable model class. The last question we have to answer is about fairness. And defining what it means to be fair is a really difficult question, and there's a lot of research in the space right now about trying to come up with the best metric for fairness. But one really common strategy is to do what's called classification parity. So in classification parity, what you're going to do is you're going to pick some sort of metric related to the performance of your model. You can think of things like accuracy, and you're going to try to make sure that that metric is equal for each of your groups. So each group in this case is just a subset of our population that we care about being fair to. So for example, in our loan classification example, maybe we care about gender. So one group would be male, one group would be female applicants. But in a lot of applications, accuracy isn't the best metric for this fairness. So this is a confusion matrix. On one axis, we have the actual response and what our predictions are. And you can see there's 2 different types of errors. We have type 1 errors, which are false positives, and type 2 errors, which are false negatives. And in our loan classification example, a type 1 error corresponds to accepting a loan that will not be repaid, whereas a type 2 error is rejecting a loan that could be repaid. And in this setting, the societal cost of the different errors are really different. If we have a type 1 error, the bank loses a little bit of money, but the bank will be fine. But a type 2 error can have a really serious impact on somebody's life. So in this case, instead of focusing on trying to keep the accuracy even across groups, it actually makes more sense to ensure that the type 2 error rate is the same across groups. So that's really the notion of fairness that we consider. And that notion of fairness is called equality of opportunity. And the idea behind equality of opportunity is we're just going to ensure that that false negative rate is even for both of our groups. Now, from a practical perspective, it's very hard to perfectly meet a condition like this, and it might not even be desirable because, as we'll see later, fair classifiers usually come at a pretty high cost in terms of accuracy. So instead, what we look at is an approximate version of this. So instead of making sure that the false negative rates are exactly even, we just ensure that the difference is within some sort of epsilon. And I'll also just mention here, for the rest of the talk, I'll be talking about equality of opportunity, but our framework can be extended to many other notions of fairness. So in our working paper, we also look at something called equalized odds. Well, you'll see that this framework is quite flexible. Great, and this gives kind of our focused research question. We're going to be trying to build these Boolean rule sets for binary classification under this constraint of equality of opportunity. So as I mentioned, because we're working in the space where we only have binarized features, there's only a finite number of rules. So the question really becomes, how do we find this optimal rule set? And for a few minutes, just suspend disbelief and assume that enumerating every possible rules isn't too onerous. So we're all operations researchers. The next step is to put this into an IP formulation. So here, the goal is to try to construct an optimal rule set. So what we're going to do is we're going to have these decision variables WK that represent whether or not rule sub K is included in our final rule set. And our goal is going to be to minimize the number of errors we make. So these epsilons are just going to track whether or not we misclassify a point. And we have two different sets of our points. We have points where the true response value is 1. We're going to call that set P. And points where our true response is 0. And we're going to call that set Z. And the majority of this model is just about adding constraints to track these errors properly. So for members of the positive class, that means we only have to add one constraint, where we essentially ensure that if we meet any, if our data point meets any rules that we've included, we can set this epsilon to 0. But for data points in our negative class, we have to have one constraint for every rule that meets. So in the worst case, we're looking at an exponential number of constraints here. The other thing that we add is this bound on complexity. So the complexity of a rule is just the number of clauses in that rule plus 1. And what we do is we put an overall cap on the total complexity of our rule set. And there's kind of two reasons for that. The first is that it acts as a tool for regularization, ensuring that we're not overfitting our data. And the other two is that it helps with this interpretability. Because obviously, if you have thousands of rules and hundreds of clauses in each rule, from a practical perspective, your rule set is no longer interpretable. Now, the issue with this formulation is really this exponential number of rules. So what we do instead is we do a little tweak, whereas instead of optimizing for accuracy, we optimize for Hamming loss. And you can think of Hamming loss as just the number of rules that need to be changed to classify everything perfectly. So for members of our positive class, it's just going to be a cost of 1 for every misclassified point. But for members of our negative class, we're going to have a cost proportional to the number of rules it meets. And the benefit of this formulation is that we now get to remove an exponential number of constraints here. It is a shortcut though, because now we're optimizing for Hamming loss, which is more of a proxy for accuracy, not the actual thing we care about. But it's a shortcut that works really well in practice. So here are some experiments where we ran with a fixed rule set, both the Hamming loss model and the accuracy model. And this is for the COMPASS data set. And what you can see is that from an accuracy perspective, the two models are more or less indistinguishable. So you can't see a difference in the distribution between the accuracy on either the train or test set using the two different objectives. But where we do see a really big difference is in terms of computation time. So the accuracy model takes, on the order of 3 to 4 times more longer to solve than our Hamming loss model. Obviously, I motivated this talk by talking about fairness. So how do we incorporate fairness? Well, Cristina kind of gave a little preview to this, but essentially all we need to do is add these two constraints that are going to bound this difference in false negative rate. The other small tweak we have to do is we have to add this constraint to track the epsilons properly. In our original formulation, if an epsilon can be 0, it will always be 0. But in the fairness case, you can have this issue where the epsilons are almost gaming the system, where it's classified properly, but we set it to 1 so that we can game these fairness constraints. So we just have to add another constraint to just catch that case. So question being, how do we actually go about solving this IP? Obviously, for non-trivial data sets, enumerating all the possible rules just creates an IP model that's way too large. So what we actually do is we use a trick from linear programming. So instead of solving the integer program directly with every possible rule enumerated, what we do is we solve the LP relaxation of the problem, and we use column generation to efficiently search over the realm of possible rules. So what we'll do is we'll start with a restricted set of rules, and then at each iteration, what we'll do is we'll solve a pricing problem to find an augmenting rule that has a negative reduced cost, and add it to the problem. And we'll repeat this process again and again until we've solved the LP relaxation, and that's to say that we can't find any rules that would have negative reduced costs and decrease the objective. And then once we have the final rule set, we solve the original IP. So this whole column generation process is essentially a rule mining operation. Now the pricing problem is also an integer program that can be a little tricky to solve. In this case, our decision variables are going to be these ZJs, which represent which features are included in the rule. Our objective is just going to be to minimize the rule's reduced cost. And we have some constraints that are going to help track whether or not we classify a point as being positive. And this lambda and these mu's are just dual values that we're going to get from solving the LP relaxation. Now, this is kind of a computational bottleneck. It's still an integer program, and for large problems, it can be really difficult to solve. So we have a few tricks and tips for just solving this more efficiently. We do rule mining, like what Ilker talked about in his talk, where we train random forest classifiers and extract rules from them. We also have a greedy heuristic that we can use to solve this pricing problem for larger instances. And then finally, for very large instances, so on the order of 10,000 data points and hundreds of columns, we also subsample both rows and columns in the pricing problem. And the question of the day is, how well does this do in practice? Well, this graph looks as kind of the efficient frontier of fairness and accuracy trade-off. So our x-axis is how unfair our rule set is. And you can think of that as just the gap in the false negative rates between our two groups. So closer to the left means a fairer rule set. And our y-axis is just going to be the accuracy on the test data. And what you can see is that in general, for all of our classifiers, there's this trade-off between fairness and accuracy. The more fair we make the model, the less accurate it becomes. But what we can see is that our algorithm, FairCG, does a really good job of dominating other fair classifiers, and that at pretty much every level of unfairness, we're able to get more accurate rule sets. And I'll mention this is on the Compass data set. And we benchmark against pretty standard interpretable fair machine learning classifiers, things like Zafar's constrained logistic regression, Hart's also logistic regression, where they choose different thresholds for each group, and then FairLearn, which is a more recent example. And in the interest of time, I'll end off here to see if anyone has any questions, either for me or the two amazing talks that came before.
Thank you very much for your colorful presentation. So I think it's time for questions. If somebody has questions, you can raise a hand or just unmute yourself. And so. Okay. Yes.
Hello? Can you hear me?
Yes, yes, perfect.
Okay. Thank you for the wonderful presentation for Cristina, Sun, and Cornell. So I got a question for Cristina because was very interesting, but was running out of time. Maybe she could spend a little more time comparing the results. I'm wondering about the comparison of this optimal method compared with the traditional things we can use in decision trees for example, CAR. I don't know how much better is this optimal tree in terms of the accuracy performance and of course, how much it costs in terms of computational time.
Okay. Thank you, Luis. I'm going to... Yes, I've been running out of time, but for example, here you can see the numerical results for classification. These are the data set that we have considered. We have used as solver the IP-opt, and we have benchmarked this our approach with DEP 1, 2, and 3, together with CARTS, which is the popular algorithm to build trees, OC1 and oblique 3, which are also greedy approaches, but implements oblique cuts, as we do. Then we have a Milo approach that at the same depth that ours. Then we have a local search approach based on this Milo approach, but they can perform trees till depth 10 and random forest. So here you can see results for depth 1 in terms of the out-of-sample accuracy, so the higher the better. And for each data set, we have the performance of this of the seven approaches. And regarding your question, you can see the average of CART, which is 82.6, and ours, which is in the end 83.9. When we go at depth 2, we also have a difference in accuracy. And well, in depth 3, we have till 2%. Well, you know that CART is a very fast method. So they are in order of second, but if you can see at the last column, we are also, well, we take more time, but it's not that bad. Yes, I don't know if you have.
Okay, yes. And I'm wondering if this difference, comparing with CAR, for example, is significant. Because 3.2, I don't know, is this something significant? Because you have an out-of-sample.
Yes, well, we have done it for 10 train test divisions, but in our paper, we have a comparison between a statistical comparison between CART and our approach in terms of accuracy and also of sparsity. So there you can find more information. Okay, it is on this one, the one that is published in IO. Okay.
Okay. Thank you, Cristina.
Welcome.
So may I ask then, Connor? Because I see that you construct the rules in advance, right? So it's how long is it? Because all of these conjunctions, disjunction could take a lot of space. Do you have any, I don't know, procedure to reduce this space?
Yeah, so great question. So a couple things. All of our experiments were run where we do this rule generation process for around 5 minutes. But a couple things we do to save both on space and time is we use things like those random forest trees as almost like a warm start to the problem. So that cuts down, we can get similar levels of accuracy in about half the time. We also, in terms of filtering rules and cutting down on storage space, we do kind of a two-stage procedure where we solve the LP relaxation and then filter to retain the top, X number of rules with the best reduced costs, and then drop the other ones as a way of kind of freeing up space and speeding up the process.
Thank you. I see you hide a lot of information on your presentation. Okay. Could I ask Asunción, because I see that this nonlinear SRAM is has a lot of different parameters, and maybe you have a special case in applications where you can't live without this method.
Where I can, sorry?
Where it's really necessary to use nonlinear SVM. So I mean, maybe you have a good example of data set which can be used.
You mean in the ones that we show in the fourth ones? Well, I think that the diabetes data set, that is not the one that I show you the details, is nonlinear. So in this one, oh yeah, this is nonlinear. I don't know if this your question.
Data set?
Yeah.
I'm not familiar with nonlinear datasets, but okay, I see your point.
Okay.
Yeah, thank you. Okay. Any questions?
No se escucha, ¿no?
Okay, it seems to me no questions. So I think maybe it's a good time to tell our presenters big thanks. It was really interesting, and it was really dense of good ideas, brilliant ideas. So thank you very much. I think I will take some ideas from your papers for my PhD. So thank you very much, and have a great week. And don't forget, our seminars are continuous. So next week we also will have next talk with Interpretable. So you're welcome to join. Thank you.